All right, last one, chapter 7. So, true or false? The electrostatic force is conservative. That's true. That's why we were able to define the potential energy. Electric field lines are always parallel to equipotential surfaces. That's false. Electric field lines are always perpendicular to equipotential surfaces. So remember, equipotential surfaces are surfaces where the voltage is constant. And because the electric field always points in the direction of the steepest decrease, so it points from high voltage to low voltage in the way that it changes the most, it has to be perpendicular to a surface over which the voltage is constant. All right, so to define a voltage at a single point, one must choose some reference point at which the voltage is zero. That's true. Normally, you can only find the change in the voltage between 2 points. But if you choose one point for the voltage to be zero, this is usually chosen as infinity, then the voltage at one point makes sense. It's always relative to whatever point you defined it to be zero at. All right, the work required to assemble a static charge distribution, meaning the work that you do or whatever that put it together did, is equal to negative the potential energy in the system. That's false. The work that you do is equal to the potential energy of the system. Now, the work that the field did, that the electric field did, that is negative. So speaking of that, number 5, the work done by the electric field as a charge moves from one location to the other is the negative of the potential energy. That is true. That's by definition of the potential energy. How is 1 volt defined? Well, we defined 1 volt to be 1 joule per coulomb. If one knows the electric potential at each point, one can find the electric field at every point. That is true. The potential and the electric field contain the exact same amount of information. The electric field points from low voltage to high voltage. That's false. It points from high voltage to low voltage. All right, short answer. Suppose our function has this form. What is the gradient of that function? Well, our function here is in Cartesian coordinates. So we'll use the Cartesian version of the gradient. So in Cartesian coordinates, the gradient is the derivative, the partial derivative with respect to x in the x direction, plus the partial derivative with respect to y in the y direction, plus the partial derivative with respect to z in the z direction. So our function was what? X squared y minus z cubed x. So the gradient then is the derivative with respect to x in the x direction. Remember, this is the partial derivative. So we hold y and z constant. So the derivative with respect to x of this first term is 2xy. The derivative with respect to x of the second term is minus z cubed. So that's all along the x direction. Plus the derivative with respect to y. Well, this is the only y here. It's linear. So the derivative with respect to y is just x squared. That's in the y direction. And then we have to add the derivative with respect to z in the z direction. Well, this is the only z here. So the derivative of this is minus 3z squared x. And that's in the z direction. All right. In general, what is the direction of the gradient of a scalar function? What? Okay, I think I said that wrong. What is the direction of the gradient of a scalar function? The gradient always points in the direction of greatest increase of the function. So it looks around in 3 directions and finds the direction along which the function increases the most and points in that direction. Draw the electric field lines and equipotential surfaces of a dipole. Okay. Well, we already drew the electric field, but let's draw it again. So if we have a dipole, we have some positive charge and some negative charge that have equal and opposite magnitude charge. So all of the field lines that start at the positive have to end at the negative. So it looks something like this. So that was bad, but you get the idea. Looks something like this. Now the equipotential lines need to be everywhere perpendicular. So if you get really close to the charge, let's draw these in red. This is just a circle. All right, sorry about that. Computer lost power. All right, so this is the electric field for a dipole. And so the equipotential surfaces have to be perpendicular to it. So if you get really close to one of these charges, it looks exactly like a circle because these lines are radially outward if you're really close. And then as you get farther and farther away, the circles get kind of squished. There's one that goes straight down. So it looks something like this. And because the electric field goes from high voltage to low voltage, these are at high voltages, these are at low voltages. So depending on how you define the voltage, maybe this is at 0 volts, then all these are increasing positive and these are decreasing negative. All right. How much work does it take to move a charge Q on an equipotential surface of constant voltage 10 volts? Well, the work that it takes you to move something the work is equal to the change in the potential energy. This is the work that you do. So this is Q times the change in voltage. Now, if you're on an equipotential surface, the change in voltage is 0. So the amount of work that it requires you to move a charge on an equipotential surface is 0. Because it's 0, this is also equal to minus the work done by the electric field. This would also be 0. An electron initially at rest accelerates over a voltage difference of 1 volt. What is its final speed? Okay. Well, we can do the same thing here, or something similar at least. So this is a conservative force, so energy is conserved. So initial kinetic energy plus the initial potential energy has to be equal to the final kinetic energy plus the final potential energy. Or if we rewrite this another way, the change in the kinetic energy is minus the change in the potential energy. All right, well, the change in the kinetic energy, we're interested in an electron that starts from rest. So we only have the final kinetic energy. This is equal to minus the change in the potential energy. So this is minus Q times delta V. So we want the speed, so we want the absolute value of the velocity. So normally we'd have a plus or minus when we take the square root, but we only want the positive because we're only interested in the speed. So this is minus 2Q times delta V over N square root. Okay. And we know all of these quantities. For an electron, the charge is negative 1.6 times 10 to the minus 19 coulombs. We're interested in a potential difference of 1 volt. And the mass of an electron is 9.1 times 10 to the minus 31 kilograms. So if you perform this calculation, you'll see that the final speed of the electron is 5.9 times 10 to the 5th meters per second. So pretty fast. This is also the amount of energy that's equivalent to 1 electron volt. Okay, how much work does it take to assemble a proton and electron from infinity such that they are 10 to the minus 10 meters apart? All right, so we have a proton and an electron. at a distance of 10 to the minus 10 meters apart. And so we want to know the work that it took you to bring these charges in from infinity. Well, let's take them in one at a time. First, let's say we bring the positive charge in. Well, that took no work because there's no other charges that we had to fight against. Next, we bring the negative charge in. So when we bring the negative charge in, we do have to fight against this positive charge. So what's that work? That work is equal to the potential energy in our system. That's 1 over 4 pi epsilon naught times each charge divided by the distance between them. So in our case, we have our constants here. The charge of a proton is 1.6 times 10 to the minus 19 coulombs. The charge of an electron is the same thing, but negative. And then we divide by the distance between them, which is 10 to the minus 10 meters. So this work or this potential energy, or the same thing, is equal to what? Negative 2.3 times 10 to the minus 8 joules. All right, so why is it negative? We can see that it's going to be negative because we have one negative charge and one positive charge. But what does it mean that it's negative? Well, we put this positive charge in first, that took no work. But when we bring this negative charge in from infinity, they're attracted to each other. So the force from the electric field is pulling our electron toward our positive charge, but we have to do work against that to keep it from falling into it. So that's why it's negative. If they were the same charge, then it would be positive, and that's because I would have to push it toward it because there would be a repulsion. Okay, for a constant electric field in the x direction, what is the voltage between 2 points separated by some distance, delta x? All right, so we have some constant field here in the x direction. So this is our electric field. And we want to know the potential difference between 2 points along the x direction, some delta x apart. All right, well, we know how to calculate the voltage. It's minus this integral. And so I need to go from this point to this point. Well, I can take any path I want to. I can take this path, or I can take this path, this path. The voltage is going to be the same. So let's take the obvious path, the one that just goes straight across. So in that case, our DL is in the x direction, and it's just dx. Right, so E is in the x direction, and our path is in the x direction. So this dot product will just give us 1. And we'll be left with the magnitude of the electric field times dx. But our electric field, we said, was constant, so this can just come out. We have the integral over dx over some length delta x. So this is just minus e to the x delta x, where this is the x component of the electric field. All right, but the way I drew it here, it's also the only component, so it's also the magnitude. All right, so what is notable about the voltage of a conductor? A conductor has a constant voltage everywhere on the surface and in the interior, at least if it's in electrostatic equilibrium. All right, time for some long answer problems. All right, so our first one has the same charges that we had in our other problem where we were doing forces. So there's one charge at the origin, there's one charge at 1.50, and then there's another charge at this location. So the first thing that we should do is draw our coordinate system and draw where all the charges are. We said there's one at the origin, that's Q1. There's one along the x-axis, that was Q2. There's one that's up here somewhere. And that's Q3. All right, and what are we looking for? We're looking for the total potential energy in the system. Okay, well, the total potential energy is equal to the amount of work it takes you to do to assemble this. These things are always going to be equal. And so the way we calculate this is by considering pulling each of these charges in one at a time. Well, if we pull Q1 in first, there's nothing for it to fight against, so that takes 0 work. Then when we put Q2 in, we have to fight against Q1. So there's going to be this 1/4 pi epsilon naught that's out in front of everything. And then the potential between Q1 and Q2 is Q1 times Q2 divided by the distance between them. And next I have to pull in Q3 from infinity. So then I'll have to fight against Q1 and Q2. So I'll have a Q1, Q3 term divided by the distance between them. Plus I have to fight against Q2 as well. Once again, divided by the distance between them. So this is R13. That is R23. And this here is R12. Okay, so how do we actually calculate these things? Well, let's do Q1 and Q2. Well, this is sort of a special case here because it's only separated in the X direction. So normally we'd have a triangle here, but these are only separated by the X. So our R12 here is just the positive version of the X component of Q2 minus the X component of Q1. Well, Q2 was at 1.5 meters in the X, and Q1 was at the origin, so this is just 1.5 meters. All right, let's do 1,3. So to find that, we'll draw Q3, we'll draw Q1, and now they make this triangle here. So it has side lengths delta X and delta Y. These are the actual differences between the Y values of Q3 and the Y value of Q1, and the X value of Q3 and the X value of Q1. So our R13 or 3,1, it doesn't matter. The distance between 1 and 3 is the same as the distance between 3 and 1. It's going to be the square root of our delta X squared plus our delta Y squared. So in our case, this is the square root of negative 0.27 meters squared plus 0.13 meters squared. So this is 0.30 meters. All right, so we have one more between 3 and 2. So Q3 is here. Q2 is way over. We do the same thing. We draw this triangle that has sides delta Y and delta X. These are actually the Y value of Q3 minus the Y value of Q2. This is the Y value of Q3 minus the Y value of Q2. So it doesn't matter which one you start with because we end up taking the square root of the squares. So it doesn't matter if these are positive or negative. So this is R32. This hypotenuse was R13. So R32 is the square root of delta X squared plus delta Y squared, which in our case, 1.77 meters squared plus 0.13 meters squared. And so this is 1.77 meters. All right, so we have everything we need now to calculate the potential energy in our system. So I say PE, whatever, I think your book calls it U. It's 1/4 pi epsilon naught times Q1. Well, Q1 was 1.5 times 10 to the minus 6 coulombs. times Q2, which was negative 2.7 times 10 to the minus 6 coulombs, divided by the distance between 1 and 2, and we found that to be 1.5 meters. If we have to add to this the term between 1 and 3, so Q1 again was 1.5 times 10 to the minus 6 coulombs. Q3 was negative 3.3 times 10 to the minus 6 coulombs. And we divide by the distance between 1 and 3, which we found was 0.30 meters. Then we have one more term between 2 and 3. So Q3 was negative 3.3 times 10 to the minus 6 coulombs. Q2 was negative 2.7 times 10 to the minus 6 coulombs. And we divide by the distance between them, which we found was 1.77 meters. All right, so if we put that all together, the potential energy in our system, which is also equal to the work required to assemble it, so I could ask this either way, is negative 0.13 joules. Okay, so it's negative because overall the system is attracted to each other. All right. So next we want to know the voltage at this point relative to infinity. All right, well, we know that the voltage of a point charge relative to infinity is 1 over 4 pi epsilon naught times the charge divided by the distance, where voltage is a scalar, so there's no direction here, it's just this thing. And if we have multiple point charges, we just add up all their contributions together. So the total voltage is going to be the voltage due to charge 1 plus the voltage due to charge 2 plus the voltage due to charge 3. So if we redraw our system here, this was our Q1, this was our Q2, this was our Q3, and we want to know the voltage somewhere out here. So this is our point P. So we just find the voltage from each one. So for instance, this distance is R2. That distance is R1. Sorry. So that's supposed to be a straight line distance. That straight line distance is R3. So we just calculate the voltage for each of these individually, and then we just add them together. Now, when we're adding our electric fields together, we had to add the X and Y parts, but the voltage is just a number. So we just straight add those. And so I'll find the voltage due to 3, but the voltage due to 1 and 2 work exactly the same way. So the voltage due to 3 is 1 over 4 pi epsilon naught times Q3 over R3, where R3 is the distance between Q3 and our point where we want to know the voltage. And so the best thing to do is to draw that again. So Q3 is over here, P is here. So this makes a triangle. Our hypotenuse is R3. And once again, this distance is delta Y. It's the difference in the Y values of Q3 and P. This is delta X. It's the difference between the X value of Q3 and the X value of P. So R3 is the square root of that delta X squared plus delta Y squared. And in our case, it's 3.16 meters. All right, so if we plug that in, our voltage due to 3 is 1 over 4 pi epsilon naught times Q3, so it's negative 3.3 times 10 to the minus 6 coulombs, divided by 3.16 meters. So this is negative 9,400 volts. Okay, so this is the voltage at our point P due to Q3. Now to find V1 and V2, you do exactly the same thing. You find the distance, and then you have the charge divided by the distance times our constants here. Okay, but I'll just leave it at that. All right, so our next part is suppose an electron is placed at this point and released from rest. What will its velocity be at infinity? Okay, well, this is the voltage relative to infinity. So we could say that this really is a delta V. It's V at the point P minus V at infinity, but we define V at infinity to be 0. Okay. So that means that the change in the potential energy between our point P and infinity is just this V at P times Q. Okay. So if we want to know the velocity at infinity, we can do what we did before. So we showed that the change in the kinetic energy is equal to minus the change in the potential energy. So this is minus Q times our voltage at our point P. And if we started from rest, our change in kinetic energy is just 1/2 mv squared. This is our final velocity. So this is minus Q via P. And we do essentially exactly what we did before. We can solve for the speed. And it's minus 2qv at our point P divided by the m times the square root. Okay, so this works for any voltage change. And if you're only concerned with your particle going to infinity, then you can just use the voltage at that point, because the voltage at a point is already relative to infinity. All right, next one. A charged spherical conductor has a constant surface charge density sigma. Use Gauss's law to find the electric field everywhere. Okay. So that's easy enough. We have this sphere. It's only charged on the outside. There's no charge on the inside. It has a constant surface charge density sigma. So there's two regions here. There's inside and there's outside. Clearly, I have spherical symmetry here. So, by the way, yes, let's give this a name. Let's call this radius capital R. So if I want to know the electric field inside, then I just draw a Gaussian surface that's inside. Say it has radius little r. All right, so Gauss's law tells us that the flux over my closed surface here is equal to the amount of charge enclosed over epsilon naught. Now, because we have spherical symmetry, this is equal to the magnitude of the electric field times the area of our surface here. That's 4 pi r squared. This is equal to the amount of charge enclosed over epsilon naught. The question is, how much charge is inside of my Gaussian surface here? And the answer is none, because all of the charge is on the surface of the sphere, and my sphere is inside the sphere. This is equal to 0. And so because of the symmetry, and only because of the symmetry, I can conclude that my electric field is 0 for r less than capital R. All right, so inside this sphere, the electric field is 0. Let's find the electric field outside. So let's redraw the sphere. Here's our charged sphere. Here's capital R. This time we want to know the electric field outside, so we'll draw our Gaussian surface encompassing this whole thing. And it has a radius little r. All right, so we do the same calculation. So once again, because of the symmetry, this is just the magnitude of the electric field times the area. And this time I have enclosed some charge. So how much charge have I enclosed? All of it. Right? All of the charge is on the surface in the sphere, and I'm outside of there. So I could either find that by multiplying the area of this sphere by sigma, this, divided by epsilon naught, or I could call this the total charge. Either way. So when I solve for the electric field outside, I have our 4 pi's here will cancel. So we'll have r squared sigma over epsilon naught r squared. And because of the symmetry, it has to be going radially outward or inward, depending on the sign of sigma. Or this is 1 over 4 pi epsilon naught times the total charge over r squared in the r hat direction. So either of these is fine. I guess technically we were given sigma, so this is better. Okay, now what am I looking for? Find the voltage relative to infinity inside, outside, and on the surface of the sphere. All right, so let's find the voltage some distance outside. So we know that the voltage relative to infinity, maybe this is at some distance r, is minus the integral from infinity to r of E dot dl. So here's our sphere, and we want to know the voltage some distance r, where r is bigger, little r is bigger than capital R. Okay, well, I can take any path I want to from infinity to this r, and of course the voltage will be constant over this sphere here. And so let's take the radial path, because that'll be the easiest to calculate. So if we take a radial path, our dr is in the radial direction, and it's just dr. So our electric field outside looks like this. So this was for r greater than or equal to capital R. So our little r is greater than capital R. So this is the electric field that I should use. Or this one if I prefer. It's in the r hat direction. Our dl is in the r hat direction. So maybe we'll use this one because it looks more elegant. We can pull all these constants out. And we'll just be left with the integral of 1 over r squared dr from infinity to some little r. So since we're integrating up to r, technically I should call this r prime, but whatever. Okay, so when I integrate this, I pick up a negative sign. Now I just have 1 over r. I have to evaluate that from infinity to r. Well, when I plug infinity in here, this is 0. So I only have to worry about the r. So the voltage some distance r relative to infinity is 1 over 4 pi epsilon naught, the total charge of our sphere over r. So this is for r greater than capital R. So I should say it's greater than or equal. So if we look at it on the surface, our electric field has the same form. It's still given by this thing. So our voltage on the surface, we just sub in capital R for little r. All right, now let's find the voltage inside. So let's redraw our sphere. This time I want to know the voltage on some little r that's less than capital R. All right, so once again, this is given by this integral from infinity to r. And I can split this integral up. Because this electric field has a different form outside than it does inside, let's have one integral over the outside and a different integral over the inside. So I can go from infinity to capital R, but only if I then go, so it's plus a negative, from capital R to little r. Okay, so this is inside of our sphere here, but on the inside of our sphere, the electric field is 0. We just calculated that. So this term is 0. So the voltage for some r that's less than capital R is just this thing. But this is exactly what we already calculated. It's 1/4 pi epsilon naught times the total charge divided by capital R. So this is for R less than capital. So the voltage everywhere on our conductor here is the same. So the voltage on our surface was 1/4 pi, the total charge over R. And anywhere inside of here, you can measure the voltage at any point and you'll get this same thing. So a conductor, and this is not special just because it's spherical, this is true of all conductors. The voltage on the surface is the same as the voltage in the interior. It's the same as the voltage everywhere, as long as we're in electrostatic equilibrium. Okay. Cool. One more. A line charge with constant linear charge density lambda has length L. Find the voltage relative to infinity, a height Z over the left end of this charge distribution. Find the electric field using the voltage. Okay. All right, so we want to find the voltage over the left end of some charge distribution. So we have a charge distributed over this line here with constant density lambda. And so we want to know the voltage here. This is at a height Z. Okay, well, we know the equation, the voltage relative to infinity is 1/4 pi epsilon naught times the integral of lambda d over R. Okay, so this is along the x direction. And let's call this spot x equals 0. Okay, so dl is the actual length of a little segment here. Since this is along the x direction, this is dx, and r is our distance from some arbitrary little dl here to where we want to know the voltage. So since this is x equals 0, this distance is x. And so our whole distance here, r, is the square root of x squared plus z squared. All right, so let's plug that in. We can also pull lambda out since it's a constant. We have the integral of dx over the square root of x squared plus z squared. So our question is, what should our limits be? Well, we started x equals 0 and we said this thing was of length L. So we go from x equals 0 to x equals L. All right, now this is a hard integral, so if this came up on the test, I would give it to you. So it's solution, keep our constants. It's the log of x plus the square root of x squared plus z squared. And then we have to evaluate this from x equals 0 to x equals L. All right. So when we plug in x equals L, the constants stick around. We have the log of L plus the square root of L squared plus z squared minus when x is 0. This is minus the log of the square root of z squared, which is z. All right, now we can combine these into a single log, where if you subtract logarithms, That's equivalent to the log of the division of the arguments. This is lambda over 4 pi epsilon naught times the log of L plus the square root of L squared plus Z squared, all divided by Z. Right? So this is our voltage at this point relative to infinity. All right, so our next part says to find the electric field. Well, it turns out that's kind of a bigger pain than I expected it to be. But in general, you can find the electric field by taking negative of the gradient of the voltage. This is kind of a hard function to integrate though, or to differentiate though. So if I give you one like this on the test, I'll give you a much easier function that you can differentiate and find the electric field from. So let's move on to the next part. It says if lambda is 10 microcoulombs per meter, the length of our line here is 1 meter and Z is 0.25 meters, then what is the potential energy of an electron placed at this point? Okay, well, we have this expression for our voltage here. So we just plug in everything for lambda, for L, and for Z. And so if you do that, you'll see that the voltage is all right, so if you plug that in, then our voltage is 1.88 times 10 to the 4 volts. We were asked what is the potential energy of an electron. So the potential energy relative to infinity is just Q times V. So we just multiply our voltage here by the charge of an electron, which remember is negative 1.6 times 10 to the minus 19 coulombs. So this will give us a negative number, negative 3.0 times 10 to the negative 15 joules. Okay, it's negative because we have this positive charge distributed over this line, and we have a negative charge here. So it's attracted to the line. And so the potential energy is negative. Okay. And what work did the electric field do as the electron was moved to this point from infinity? Okay, well, remember the work that the field does is always minus the change in the potential energy. Well, the potential energy at infinity is negative. So we only have to worry about the potential energy at this point, or is 0 at infinity. So that means the work that the electric field did in moving the electron from infinity to this point where we found the voltage is positive 3 times 10 to the minus 15 joules. All right, thanks guys.